All right. So today we discuss about the frequency domain representation of AM, and we talk about the power, single sideband and double sideband amplitude modulation. In frequency domain, if we want to show the amplitude modulation, so as we seen in the previous slide, we will have upper sideband and lower sideband and the carrier frequency. So these are parts of the amplitude modulation. So these can be seen by a spectrum analyzer, or in theory or in simulation you can use something like, for example, fast Fourier transform. So here is one time domain representation of amplitude modulation. The first graph is showing amplitude modulation, so you can see the envelope shown by dash. So the second graph, which is in red color, is showing you the modulating signal. So the signal that we wanted to modulate. So it is a sine wave, which after modulation, you can see the envelope. So the carrier is the higher frequency, the blue color here in the first graph. And the peak of the carrier now is same shape as your modulating signal. So then the other three waves are your modulated signal, or they show, in fact, their frequency. So the middle one is the carrier frequency. The lower sideband is the blue color, which should have a slightly lower frequency than the carrier. And the last one is like a orange or brown color, is upper sideband signal, which should have a slightly higher frequency compared to the carrier. And from here, if you follow my mouse, in the right side, showing their amplitude or power and their frequency. So you can see the carrier is in the middle, the highest power. The two sidebands are away a little bit, depend on the frequency of your modulating signal. Let's say if your modulating signal is 10 Hertz, so your spectrum or frequency, the upper sideband or lower sideband, will be 10 Hertz away from the carrier, means 10 Hertz more than and 10 Hertz less than the carrier frequency. And you can see the power is quite smaller. So that is something which we will discuss shortly. So here it's showing the bandwidth. The bandwidth is the difference between the upper and lower sideband frequency. So that represents your bandwidth. So here in this example, the upper and lower sideband of a voice modulator AM signal is presented. So the central line, which shown by FC, is the carrier frequency. Here is 2800 kilohertz. Then you have upper sideband and lower sideband. So your voice started, in fact, having 300 hertz up to 3 kilohertz. And then if you look at here, the upper sideband started from somewhere 300 hertz and going up to 2803 kilohertz, which is 2800 plus 3 equal to 2803 kilohertz. So if you look at here, there is written FC plus 3. So means whatever is your carrier is plus 3 kilohertz, which is the highest frequency of the voice in this example. So that's why it become 2803 kilohertz. For the lower sideband, we have again same equation, but here will be subtracted. So 2800 kilohertz is our carrier frequency minus 3 kilohertz, it becomes 2797 kilohertz. So the bandwidth here is the highest frequency minus the lowest frequency, which is 2803 minus 2797, it becomes 6 kilohertz. Or the bandwidth is 2 times the bandwidth of your modulating signal. 2 times 3 kilohertz is 6 kilohertz. So either of this method you may use to find your bandwidth. So here the bandwidth we calculated is based on this equation, which is upper sideband frequency minus the lower sideband frequency. So this is upper sideband frequency 2803 and the lower sideband frequency is 2797, which result in 6 kilohertz. So this is how you can calculate your bandwidth of modulated signal. I have one more example here. So we have a standard AM broadcast station is allowed to transmit modulating frequency up to 5 kilohertz. If the AM station is transmitting on a frequency of 980 kilohertz, compute the minimum and maximum upper and lower sidebands and the total bandwidth occupied by the AM station. So our carrier frequency is 980 kilohertz. And we can transmit up to 5 kilohertz. Probably this is for voice communication, which is usually up to 3800 hertz or 3.8 kilohertz. So they consider 5 kilohertz, so to have a little bit gap between different channels. So then our upper sideband is 980 plus 5 is 985 kilohertz. Our lower sideband frequency is 980 minus 5 is 975 kilohertz. Then the bandwidth is upper sideband minus lower sideband. So 985 minus 975 is 10 kilohertz. Or 2 times 5 kilohertz, which is modulating frequency, is 10 kilohertz. So then here it is showing frequency spectrum of AM broadcast for this example, related to this example. So each channel has 10 kilohertz bandwidth. So you can see the carrier considered for each of them is at the center. For example, 540 kilohertz is the carrier. Then the bandwidth is plus minus 5 become 10 kilohertz, the total bandwidth. So the next channel is 550 kilohertz carrier. So next one is 560 kilohertz and going on. So this 980 can be somewhere in the middle, for example. So that is how we're using different carrier frequency to modulate different voices. And then we can do a frequency division multiplexing and transmit them. I think it's good to show you a little bit how these upper sideband and lower sidebands come from. So here it is, which I am showing you. So if I show you just a sine wave, here I am showing you a cosine omega m, so omega mt. So it's just a cosine waveform. It has an amplitude of am, and means the peak voltage of this sine is am. Frequency is fm, or it becomes 2 pi fm, shown by omega m. Of course, it's changing by t. This is a time domain signal which I am showing by xt. If I convert this to frequency domain by applying Fourier transform, so the xt become xf. So now we are talking the frequency domain. So then my amplitude am become half, become am over 2, and cosine omega t become 2 delta f. If I show you or plot this frequency spectrum, you can see in this figure I am showing you, the x-axis is frequency and the y-axis showing the amplitude of the frequency spectrum, which is here am over 2. So, and there are two impulses which we call them delta. So what is frequency of them? One of them is f equal to fm, means this is f equal to fm, which is this. And another one is f equal to minus fm, which is this one. So means this is the upper sideband, this is the lower sideband. And that's why you can see, because of the cosine, you have two bands or two delta here. This is something what you can see here as well. So you can see if you have a carrier, there are two peaks in the two sides. But here what I am showing you is just a one cosine waveform itself. Okay, so if you understand this, I can show you one step more. If we have a signal, so here is just cosine. I show you in cosine in time, what would be in the frequency domain. So each cosine waveform will provide you two impulses in the frequency domain. Now, assuming I have a modulating signal, let's say, which is xt. Let's say we don't know what is xt. Don't take this xt here, same as this xt. No, they are two different signals. See, this is just example. This could be, maybe I could write empty, or I should write anything else. But here I just show, assuming xt is my modulating signal, I multiply this by a carrier of cosine omega ct. This omega ct now, let's say, is carrier frequency, which has much higher frequency compared to my modulating signal. And assuming the whole signals have an amplitude of AC, if I convert this to frequency domain, or I get a Fourier transform of this, my amplitude become half, AC become AC over 2. Then my xt become xf, and then I have f plus fc and another x f minus fc. So my xt become xf. So what happened to delta? Here I had a delta when it was just a cosine. But when there is a signal multiplied by cosine, then it becomes just the signal spectrum, so that which is xf plus fc and xf minus fc. So assuming this is a frequency spectrum of xt alone before modulation. After modulation, what happened is we will have the amplitude dropped, become half. You can see AC over 2. Then you have two spectrum. One is in the positive side of your carrier, or the upper side. Another one is in the lower side. Then we call it upper sideband and lower sideband. The bandwidth you need to transmit your signal is 2 times of your original bandwidth. So this is also something maybe helpful for your understanding. Now in my next slide, I want to show you an amplitude modulation, which we have learned in our earlier slides. So this is not amplitude modulation. In fact, is another modulation. We call it double sideband suppressed carrier modulation, which I will show you a little bit later on my slide today. But I just put for you here to understand when a signal multiplied by cosine, it will give you this form in the frequency domain. So, and I wanted you to compare this when you have a cosine without any signal. If there is a cosine itself, it's just two impulses. When the cosine is multiplied by a signal, it will follow the signal bandwidth or shape. But now here I have amplitude modulation. In time domain, as we shown, is a carrier, maybe something like this. This is one example of AM. In the frequency domain, what we have is this form, which is, okay, let me show you this this equation, I guess, is helpful if it is shown here for you. So if I multiply my cosine, which is my carrier, multiply by this equation, I have one cosine, which is like this, it's just the carrier. Then cosine times xt, which is modulating signal, then which should have two parts, upper sideband and lower sideband. So, but this is shown in time domain, in fact. If now I show you in frequency domain, my signal, when I multiply cosine with 1, means only this part, which is sine wave, but here I'm showing you cosine wave. So the cosine wave producing 2 delta, which is delta f plus fc plus delta f minus fc. This comes from the first part of your equation, or only the carrier. This only representing the carrier signal, which is cosine times 1 here. So the other term is cosine times amxt. So as I show you in the previous slide, cosine times xt give you also two parts, which is, here is am times xf plus fc plus x f minus fc. So this is also have two parts which relate to upper and lower sideband as well. If I show you this, and assuming my xf, if this is xt, this is xf, assuming this was my spectrum or frequency of my xt, so this is xt in time domain, this is xf, showing how is the frequency spectrum of your signal. So this is only for modulating signal, before modulation. After modulation, what happened to this spectrum? It will be shifted, or will be two copies, one in the upper sideband and another for lower sideband, and following your carriers. So you can see now you have two of these shapes. One is in the higher frequency, another in the lower frequency. So, and there are at the middle, there are two impulses, which in fact are the carrier, which comes from the delta. So this delta comes from this signal, which is sine wave, or here is a cosine wave. So they are almost the same, with a slightly different in the calculation, but for your understanding, easier to use a cosine for me to show you. So your frequency domain is like this. So you have your modulating signal spectrum has been shifted, and there is also a carrier at the center of them. Of course, by right, I should show this carrier at the top, because the spectrum should be combined together. But here I just show you what they mean. But otherwise, this carrier should start from the top of the spectrum towards up. So, okay. I hope you understand this, but these are not available in the textbook we are using. but you can find this in other textbooks. This is good for you to understand each of signal you are sending, there is a carrier with them. So which is our next topic we want to discuss. So most of the power in your communication, amplitude modulation transmission is in the carrier. However, your sidebands or your information has very low power. If you look at here, xt is my modulating signal. I want the xt at the receiver. Your carrier carries more power compared to your modulating signal or the message. So let's see, understand more. After this, I will explain a little bit more on the power. So what is pulse modulation? So what we mentioned so far was mainly modulating a signal which is like a sine wave or cosine wave, or we call it tone modulation. They have one fundamental frequency. So now we want to talk about pulse modulation, which has a little bit different frequency compared to a sine wave or tone modulation. Tone modulation, they have one frequency, which is fundamental frequency. But when we talk about pulse modulation, they may have more or frequency components, or we call it, they have higher harmonics or frequency. When complex signals such as pulses or rectangular waves modulate a carrier, a broad spectrum of sidebands is produced. Modulating a square wave will produce sidebands based on the fundamental sine wave, as well as the third, fifth, seventh, and other higher frequency harmonics. Depend on what bandwidth you want to define. If your bandwidth is limited, the higher harmonics will be lost or won't be passed from your system. They will be highly attenuated. Amplitude modulation by a square wave or rectangular pulses is referred to amplitude shift keying or ASK. So ASK is used in some type of data communication. Okay, so this is frequency spectrum for a carrier which is modulated with a pulse modulation. So you can see the fundamental frequency is here, which when we have a sine wave, usually we have only this because they have only one frequency element. Then this is a third harmonics, upper sideband and lower sideband. Fifth harmonic, seventh harmonic. You can see the power is reducing. Fundamental frequency have higher frequency. Third harmonic has lower frequency. Fifth harmonic is lower. Seventh harmonic is lower. Depend on how much power you need in your receiver, you can adjust your bandwidth. If you open your bandwidth a little bit more, you can receive more power, let's say up to third harmonics, for example. But of course, if you open your bandwidth more, you also receive maybe a little bit more noise, and your system will be a little bit less efficient because the bandwidth is one of the very important part of your system and the most expensive part of your system. So that's why we try to avoid having large bandwidth just for a little bit power. We prefer to transmit more power rather than having more bandwidth. So, but of course, there is a trade-off between bandwidth and power. Sometimes the bandwidth is not very important. Power is very important. For example, when we do satellite communication, the transmission between, let's say, two satellites, they don't need, the bandwidth is not limited there because there are no other signal transmission maybe there. But the power is very important for them because they have limited power up in the space. So for them, maybe they can use a communication with larger bandwidth because there they have more bandwidth, but they have less power. But on the Earth, when we are transmitting, we can easily increase the power, for example, between two antennas, but the bandwidth might be limited because there are other communication going on around us, which they are occupying the bandwidth. So here is time domain representation of your pulse modulation or rectangular wave, which we want to modulate this. When we modulate a carrier based on amplitude modulation, or here we call it ASK, amplitude shift keying, then the envelope of your carrier or your modulated signal become this shape. You can see the amplitude is higher at this point where the power is high. Then the amplitude become lower where the power is low. This is for a modulation where the modulating index M is not equal to 1, is smaller than 1. So, and the second graph showing you also amplitude shift keying or AM modulation for rectangular wave, but here the modulation index is 1 or 100% modulation index. So in this case, your signal has higher power or amplitude at these points. Then for here, there is 0 or become no power. So if you look at here, the amplitude difference in the second case is higher. Compared to here, the amplitude difference is less. So at the receiver side, it is easier for you to distinguish between the, for example, let's say this is, let's say we call it binary. This is 1 representing 1. This is representing 0. So then the difference between these two voltage would be higher in your receiver. So here is saying in this case we have 50% modulation, and in case B we have 100% modulation. So we prefer higher percentage of modulation index. So like here 100%. So this is, we call it ASK, when a carrier modulating a rectangular or pulses. In radio transmission, the amplitude modulation signal is amplified by a power amplifier. A radio antenna has a characteristic of impedance that is ideally almost pure resistance. The amplitude modulation signal is a composite of the carrier and the sidebands, which we have two sidebands. Each signal produces power in the antenna. So both carrier and the sidebands produce power in the antenna. Total transmitted power, we show by PT, is the sum of the carrier power, PC, and power of the two sidebands, P upper sideband and P lower sideband. So, which is shown like this. P carrier plus lower sideband plus upper sideband. I can show you a little bit more mathematics to get a final equation which relate your carrier power and modulation index. Then you can find your total power. So here, the carrier power and the two sidebands, I am relate these to your equation we have shown you earlier. So our signal after modulation is equal to, here showing the voltage, is Vc sine 2 pi fct plus Vm over 2, which is our modulating signal voltage. So it become half. So it has been multiplied by sine. So then we had Fc and Fm, we broken them in two parts, become cosine wave. So that on two parts, we have Vm over 2 cosine 2 pi t with frequency of Fc minus Fm minus Vm over 2 cosine 2 pi t Fc plus Fm. So we have two parts of our sidebands. So this is lower sideband, this is higher sideband. So then Vc and Vm are peak value of our sine and cosine waves. However, power in base RMS value. So we need to divide this by a square root 2. So we divide them by a square root 2, each of the voltage, the peak voltages. So then we have this form, and power can be calculated based on this, which is voltage square over the resistance of your system. So to do this, what we need is, we say our power is equal to this, the signal or voltages divided by the resistance of our system, or here perhaps is our antenna. Then these sine waves, in fact, doesn't come into your equation. We can consider the maximum value where the sine become or cosine become 1. If we consider them, so then sine and cosine terms can be go out. When we want to calculate the power, we take the magnitude of the voltage, and assuming they have maximum value, no phase, so then we have 1, 2, 3 terms here. We combine them. For power, we are just combining the total power. So this is for carrier, and these two are for the sidebands. Then we have 3 terms, simplified the values. So a square root 2, power 2. So it become then 2 here. 2 times a square root 2 power 2, then it become 8 here. So you have carrier voltage square divided by 2 times your resistance, plus for the two sidebands, you have the peak of your voltage power 2 divided by 8 times your resistance. And this is repeated 2 times for the two sidebands. Of course, both sidebands have same powers. So now we consider our modulation index, which we said is our modulating signal voltage divided by our carrier voltage. Then I can replace this with Vm, the voltage of my modulating signal. So then I have modulation index times the voltage of the carrier. So then I substitute Vm here with M times Vc in this equation. So what I have then, I change Vm with MVc. Then I have this equation now. So these two combine together and I get factorial from 2r and Vc. What left is 1 plus m squared over 4, repeating twice. And then if you combine these two, become 2 times m squared over 4 or m squared over 2. So that is your equation. If you have your carrier power and your modulation index, without knowing what is the power of or amplitude of your modulating signal, you can calculate the total power in your modulated signal. So finally, we have a formula for computing the total power in an AM signal when the carrier power and the percentage of modulation are known. So let's we have few examples. If the carrier of an AM transmitter is 1000 watts and it is modulated 100%, means M equal to 1, the total AM power is 1000 times 1 plus modulation index squared divided by 2. So here 1 squared is 1 over 2 is half, plus 1 is 1.5 times 1000 is 1500 watts. Of the total power, means out of 1500 watts, 1000 watt of it is in the carrier. That leaves 500 watt in both sidebands, means combining two sidebands, the power is only 500 watts. Since the sidebands are equal in size, each sidebands have only 250 watts. Remember, when you receive the signal, the power, you need the sidebands to get your message, because the message is in the sidebands, not in the carrier. Carrier carries the most power, but have no information. For 100% modulated AM transmitter, 100% means the best condition. The total sideband power is always 1/2 that of the carrier power, or 50% of the carrier power. So means 50% of carrier power we have in the whole sidebands, means both of them. In other words, 2/3 of the transmitted power is in the carrier and 1/3 is in the sidebands. So like here, 1500 is the whole power. 2/3 means 1000 goes for the carrier, 500 goes for the sidebands. Another example, a 50 kilowatt transmitter carrier that is 100% modulated will have a sideband power of 25 kilowatts. So with 12.5 kilowatt in each sideband. So we have 50 kilowatt transmitter carrier. So this is only the carrier, 50 kilowatts. Half of this is for the sideband, means 25 kilowatt. Each sideband has only 12.5. The total power for the AM signal is the sum of the carrier plus the sidebands, means 75 kilowatts. So when the percentage of modulation is less than the optimum condition, means less than 100%, there is much less power in the sidebands. Let's see one example. For a 70% modulated 250 watt carrier, the total power in the whole AM signal is 250 watt carrier times 1 plus modulation index square. Here is 70%, means 0.7 square over 2. 0.2 square over 2 gives you 0.245 plus 1 multiplied by 250 is 311.25 watts. This is the whole power. If you subtract carrier power, so 311.25 minus 250 watt carrier power, you have 61.25 watt in the sidebands. How much is each sideband having, power? 61.25 divided by 2, you have only 30.625 watt in each sideband. You can see out of 311 watt, you have only 30 watt in each sideband. When your modulation index is less than 100%. So another example here, an AM transmitter has a carrier power of 30 watts. The percentage of modulation is 85%. Calculate the total power and the power in one sideband. So how we calculate the total power? Using this equation, carrier power times 1 plus modulation index square over 2. So I have 30 times 1 plus 0.85 square over 2. I have then 40.8 watt as the whole power of the carrier and sidebands. So then I have total power, I have the carrier power. If I subtract, I have 10.8 watt in the sidebands. If I divide by 2 this, 5.4 watt power I have in each sidebands. So that is how we can calculate the power in AM modulation and the sidebands. In the real world, it is sometimes difficult to determine AM power by measuring the output voltage and calculating the power with the expression we have, which is V square over R. However, it is easier to measure the current in the load. So if we want to use load, the current in the load, we can use this equation, which is PT, the total power, equal to the total current square times the resistance of your RF system or antenna. So IT is measured RF current and R is impedance of the antenna. And IT is equal to IC, which is the carrier, unmodulated carrier current in the load. So is IC square root of 1 plus M square over 2. So then our IT is based on this equation. So you have 1 plus M square over 2 plus 1 square root of this. So it's a little bit similar to our previous equation, but now is calculated based on current. So an M is modulation index. In this example, we have the total output power of an 85% modulated AM transmitter whose unmodulated carrier current into a 50 ohm antenna load impedance is 10 ampere. So means our unmodulated carrier current is 10 ampere going through an antenna having an impedance of 50 ohm. So we have the current of unmodulated carrier. We have the percentage of the modulation index. So then we calculate the total current, which is 10 times a square root of 1 plus 0.85 square over 2. We get 11.67 ampere total current. Then we use this equation, the total power equal to total current square times the resistance or impedance. So 11.67 square times 50 ohm, we get 6,809 watt power. So, or in another example, we have the unmodulated antenna current of 2.2 ampere. That is the current produced by the carrier only, or IC. Now, if the modulated antenna current is 2.6 ampere, so this is modulated antenna current, which is 2.6, means the total current. The modulation index can be calculated as well using this equation. So means now we have the total current, we have carrier current, we are looking for the modulation index. So we solve this equation for the modulation index. So then we have M equal to a square root of 2 times the total current over the unmodulated current square minus 1. So then we can find our modulation index, which here is 0.89 or 89%. So this is also maybe another form of calculation you may have in your course, for example, or in your subject. So, okay. So now we talk a little bit more on the power related to the spectrum. Here we can show by a spectrum. the greater the percentage of modulation, the higher the sideband power and the higher the total power transmitted. So power in each sideband is like this. So means sideband power means one sideband power is equal to either lower sideband or upper sideband. Both of them have same power, equal to carrier power times modulation index square over 4. So you can see here, this comes from our previous equation, which is this equation. So if you multiply this or earlier equation which we had, so you have carrier power, this is one sideband and this is the other sideband. So when it comes to the power, you have carrier power, which is VC square over 2R, and times 1 plus the two sidebands. So what you see there is PC times this divided by 4, one of this. So that's why you can see PC times M square over 4 representing one sideband. Maximum power appears in the sidebands when the carrier is 100% modulated. So make sure, remember this. This is for maximum power when the index becomes 1, for example. So, or this means the maximum power we can achieve is when the sideband has a 100%, I mean the modulation index is 100%. That is the maximum power we can have in our sidebands. So let's have another example. If the carrier power is 100 watts, then at 100% modulation index, 50 watt will appear in the sidebands, 25 watt in each sidebands, while the total transmitted power is 150 watts. As we mentioned earlier, the carrier power percentage is 100 over 150 is 66.7%. The sideband power is 50 over 150 is 33.3%. Means 2/3 of the power goes for the carrier, 1/3 goes for the sidebands. So this is 33.3 is for the whole sidebands. Each sideband has half of this. So now is your turn to have few examples. So in this example, we have an antenna which has an impedance of 40 ohm. An unmodulated AM signal produces a current of 4.8 ampere. The modulation is 90%. Calculate the carrier power, the total power, and the sideband power. So I give you 2-3 minutes. You solve this, and then I will show you the calculation and the answer. Okay, let's see how we can answer this question. So for part A, to find the carrier power, we use P equal to I square R. We have the current of the unmodulated carrier, which is 4.8 ampere. We have the antenna impedance, which is 40 ohm. So 4.8 square times 40, we have 921.6 watts. For part B, the total power, we can use this equation IT equal to the carrier current times a square root of 1 plus modulation index square over 2. So we have 4.8 ampere for the carrier times a square root of 1 plus modulation index is 0.9, which is 90%. So this is a square over 2. So then we have 5.7 ampere as the total current. This total current means the current of carrier and after modulation. So, and the signal, modulating signal. So then the total power is then IT squared times R, 5.7 squared times 40. We have 1,295 watts. Then the sideband power is total power minus the carrier power. We have 373.4 watt in the sidebands. If we want to know the power in each sideband, then we divide this by 2, become 186.7 watt for each sideband.